right now, beneath the surface of what look like perfectly healthy farms, crops are actually secretly starving.
Right.
And, the crazy part is they're completely surrounded by food. Welcome to the deep dive. Today we're looking at agricultural product data that reveals this huge hidden problem in modern farming.
Yeah, it's a massive paradox, especially when you look at phosphate. I mean, phosphate is an absolutely vital macronutrient for crops, right? But it is notoriously one of the most locked-in soil nutrients on the entire planet.
Locked in. So meaning the plant just can't get to it.
Exactly. Only, well, about zero point 0.1 to maybe 1% of the phosphate actually in the soil is available for plants to use. And even when farmers apply, heavy phosphate fertilizers, the crops only absorb like 10 to 20% of it.
Wow. Only 10%. To me, it's like having $1 million in your bank account, but you've completely lost the debit card. Like the wealth is physically right there under your feet, but it's just utterly inaccessible.
That is a perfect way to put it. And today's sources point to this really elegant biological solution for this exact problem. It's a biofertilizer product called Pseudomonas. And we aren't just talking about, a single microbe here.
Right. It's actually two strains, isn't it?
Yeah, exactly. It's composed of two highly synergistic strains that work together. So you have Pseudomonas fluorescens and Pseudomonas chlorophyll.
And they basically operate like these microscopic locksmiths, starting with how they tackle mineral traps in the soil. Because phosphate rapidly forms these incredibly strong, insoluble bonds with positively charged molecules, right?
Hmm.
Like calcium, iron, aluminum.
Right, sulfications. The plant just cannot pull those bonds apart on its own.
But the Pseudomonas bacteria can.
Yeah, they break these mineral bonds by producing organic acids. Specifically, we're talking about gluconic, citric, and oxalic acids, along with these iron-chelating compounds called siderophores.
Cytophores.
Yeah, they basically act like microscopic claws to just pry the iron away from the phosphate.
Wait, hold on a second. Releasing acids directly into the soil, that sounds highly destructive. I mean, wouldn't a local acid wash just burn the very plant roots we're actually trying to help?
I know, it sounds bad, but it's really a matter of scale. This isn't some widespread acid bath, it's precision chemistry.
Oh, okay, so it's microscopic.
Exactly. These bacteria have what's called a phosphate solubilization index, or PSI, of 7.1, which simply means they safely free up a targeted zone that is exactly 7.1 times larger than the bacterial colony itself.
Ah, got it. Okay, so it's a highly localized, safe reaction for those mineral bonds. But, soil isn't just rocks and minerals. It's packed with dead plant matter and complex organic molecules, stuff like phytates and phospholipids.
Right, the organic debris.
Yeah, and plants can't directly absorb phosphate when it's locked up in that stuff either, right?
No, they can't, which is why these microbes deploy a completely different mechanism for those organic traps. They produce very specific enzymes, primarily one called phosphatase.
Okay, phosphatase.
Yeah, and these enzymes act like tiny biological scissors. They literally snip the plant-available inorganic phosphate right off of those complex organic molecules and just release it into the soil.
That's incredible. But, freeing the phosphate is obviously a huge feat, but it's practically useless if the plant's roots are too short to reach it, right?
Right.
Because from what I understand, phosphate is incredibly stubborn in the dirt.
Oh, absolutely. It only naturally moves about maybe 3 to 5 millimeters a year in soil.
3 millimeters a year, so the plant physically has to grow out to find the food.
Exactly. And our two strains solve this by acting as plant growth promoting rhizobacteria, or PGPR for short.
Ah, PGPR. So they aren't just acting as soda mechanics, dissolving the nutrients. They are actively communicating with the plant's own biology to stimulate growth.
You hit the nail on the head. They produce plant hormones, specifically auxins and cytokinins.
Oh, wow.
Right, so instead of the plant having to synthesize all these signals itself, the bacteria just supply them, which triggers rapid root elongation and branching.
So the plant builds this much larger, denser root system, which massively increases its surface area to just, hunt down all that newly freed phosphate.
Exactly. We spend so much energy and money trying to force nature to yield through brute force chemistry, and we often get diminishing returns. But nature already has these elegant, highly efficient mechanisms in place.
Yeah, it's amazing. These two strains, they don't just blindly dump nutrients into the dirt. They're functioning as both microscopic chemists and growth hackers all at once.
Yeah, they really do pick the chemical locks to free up both mineral and organic phosphate and then physically build bigger plant roots to absorb it all.
It's wild.
Yeah.
And leaves you wondering, if microbes can effectively pick the chemical locks of the soil to feed our crops and boost global yields, What other massive global resource crises might be solved by simply partnering with the invisible microscopic ecosystems already functioning right beneath our feet?